All right, one more round of some ideas, just some basics for some trig stuff. So thank you for coming all week long. I really appreciate it. Just want to show you a couple things that happen mostly in 4.3. So if you wanted to give yourself some direction as to where to look for stuff like this, it'll happen in 4.3. And I'll give that a title here in a second, but I wanted to kind of lead you into it in a way that hopefully kind of ties in the stuff that we've been doing before. Okay. First things first. I'm going to focus just on first quadrant space. Okay. All this stuff can be applied to any quadrant, but I really want to focus mostly on kind of a first quadrant. So let's call it quadrant 1 focus. Okay, where everything's nice and positive. Okay, x's are positive, y is positive, so that means cosine and sine are all positive, which means everything's positive, right? So I'm going to have a kind of a first quadrant focus in here, and I want to start creating an understanding for you of how we can connect something. So think about it like this. I'm just going to call this one number 1. I don't know, I'm going to make it up. Let's say like the cosine of theta is 1/2. Let's say they kind of lead with, for the first time, an equation with something that we don't know, okay? And they want us to kind of answer that question, what angle is going to make that work, right? And so if I'm in the unit circle somewhere and I get nice ratios like this, I should be able to find a first quadrant spot for that. And just to hopefully, hopefully this makes sense to you, but all right, cosine is x. So I'm really just looking for an x value for an angle that gives me 1/2, right? And of course that's pi/3, right? That's pi/3 radians, okay? And that's how questions like that would shake out, right? And they can ask all kinds of questions about the first quadrant that have really, really, really nice unit circle spots, right? Sine of theta is radical 2/2 or something like that, right? Where they give us not just some expression to evaluate, but an equation to solve, right? And what I want to give you is the mindset that's happening kind of in between here, and maybe a way to write this stuff down so that you have kind of a step of work happening in between. Okay, and I don't know that you really need to know that this step is like critical to write down. As long as you have a good mindset, I think I'm good. If I want to get theta by itself and it's got a trig function attached to it, right, sine of something, I need to undo that, right? And just like if this was 3x equals 12, right? Okay, 3x, so that's 3 times x. I'll do the opposite. Okay, I'll divide by 3, and yay, x is 4, right? X plus 7 equals 19. Okay, I'll subtract 7 on both sides, right? I'll do the opposite of what's there. Well, what's here is sine. And there's an opposite of that, right? Every trig function has its inverse. And what we can do is we can take the inverse sine of the left-hand side. Because if I take the inverse sine of sine of theta, I've got a function and its inverse, and they'll cancel each other out, right? If I have multiplication, I'll have division, and those are opposites, so that'll cancel each other out. Squares and square roots, everything has its inverse, right? Same thing is true with trig, okay? But whatever I do to the left, I better make sure I do to the right. Right? And so theta really is, right, because inverse sine of sine, those will just cancel out because they're exact opposites of each other. Theta is really just me asking the question, okay, what's the inverse sine of radical 2/2? And that's what we did yesterday, right? We started to look at some inverse stuff, and we know we're going to get an angle back from that inverse sine of radical 2/2 in the first quadrant. I'm just going to keep us there for now. That's exactly 45 degrees, right? That's exactly pi, right? And kind of these two steps in between here, I think are honestly really optional. if we're starting with a function and we just know what we're looking for and how to do that, right? But I just wanted to make sure that I showed you that there is this step of algebra, this trigonometric algebra that you can write in between, which is great, right? But if you don't need it, I'm good with that, right? Again, this was just a first quadrant focus, so I'm not going to say, oh, you know, it could be pi over 3 or 5 pi over 3, or pi over 4 or 3 pi over 4. Right? We had those two possibilities yesterday. I'm just focused on the first quadrant right now because the kind of question that they might ask could look like this. Okay, what if it was sine of theta equals some ratio that doesn't show up at a pi over 6, a pi over 4, or a pi over 3 kind of spot? Like, what if they said the sine of theta is 3/5? Now, that possibility is okay, right? Because remember, the range of sine, just like the range of cosine, is just -1 to 1. So as long as that number fits within that range, I've got an answer somewhere, right? But I really don't know where, right? So if I'm in the first quadrant, right, I'm looking at a space in here where the y value, so if that's 1 up there, the y value, call it like 3/5, like, you know, 0.6, like right there, I've got some angle that I've opened up that has some y value of 3/5. And really, I don't know what that angle is. And you could jump into the calculator and see what happens. Let me do that real quick so you can see that, yeah, the angle exists, but it's not necessarily going to be the kind of angles that we're hoping to see. I'm really hoping for better angles than these 3/5. Yeah, it exists, but where, right? And so I just kind of wanted to give you a background on this and then what we can do with these ideas, right? So I don't know. Okay, the inverse sine of 3/5. I'm in degrees, so I should get a degree measure back. Ugh, yuck, right? 36.869. It's just some nice. It's irrational, but it is some answer. And so, like, what do you think? What do you think we could write as like the best version of theta? If we get this, you know, this inverse sine of -3/5 gives us of 3/5. Sorry, the inverse sine of 3/5 gives us this irrational looking degree measure. See if you can think about it. What angle? Like, what's the best way to write theta if that's what we're getting? Any ideas?
Inverse sine of 3/5.
Exactly, right? And that, like, the steps that we did in between here kind of gets us to that same point, right? That if I were to just kind of solve this equation, I would take the inverse sine of the left, which means I would have to take the inverse sine of the right, and we end up with some theta. I don't really know what it is. Better than just saying the inverse sine of 3/5, okay? And great, that's just some angle, and it's approximately something, right? 36.8699 degrees, right? And great, cool. But what good does that do, right? Well, number one, it gives me an exact value for irrational degree measures or radian measures. That's cool too. But what are we going to do with it from there? Okay, that's what I want us to get to. So number one, we have a way to write angles that aren't necessarily perfect, as long as we're given some nice equation to begin with. Okay, but what I want to do from here, again, I want to focus just on the first quadrant. Okay, but I want to start breaking us out from the unit circle to be able to draw images of these angles in a shape that might lend itself better to us than dealing with a circle, okay? And remember what we did kind of from the beginning. You know, we draw an angle right there. There's my theta that's this exactly, right? So I know that this location is 3/5 for y. Let me ask you this. Where's x? What's the cosine of that angle? All right, so if they give us, and I'm going to start moving over here a little bit, leak onto the next board. Okay. Still here in number 3, if sine of theta is 3/5, what's cosine theta? How can we start relating one trig ratio to another? Well, what I really care about is that value right there, right? That x distance away from 0. And so what 4.3 tries to get us to realize is where all this stuff came from when we went back to the very beginnings of all this. And we started to draw shapes inside those circles to give us a better understanding of what those distances are, right? What we can draw are right triangles. Okay. 4.3 is right triangle trigonometry. Right triangle trig. I just kind of wrote a little right triangle trig up in 4.3. Okay. So how do we do that? Right. What basic setups do we have within right triangles? And I, in the first quadrant, am always going to draw my right triangles in this orientation. Okay. Imagining that this bottom left-hand corner is the origin, okay? And that the right angle is going to happen over here on the right side, okay? That's going to still be that radius of this right triangle. But what can we do with that? What can we do with a setup that looks like this? Well, maybe we do ourselves a favor, right? Maybe we say, you know what? This whole unit circle thing has been really nice for some really nice values, you know, 30s and 45s and 60s and 90s. You know, I can't even draw a right triangle if I'm up at 90 degrees, not from the center. But what we can do is some basic right triangle trig to answer questions that look like this. Okay, and that's what I want to do. So maybe you remember a nice series of letters that help us understand what sine means in a right triangle, what cosine means, and what tangent means. Maybe you remember from geometry. SOHCAHTOA. Okay. The fact that sine of an angle is the length of the side opposite over the length of the hypotenuse. SOH, right? That cosine of theta is adjacent over hypotenuse, and that tangent is opposite over adjacent, right? You probably walked out of geometry knowing that, right? And certainly from last year, if you took Algebra 2 Trig, we've got a setup for sine. I know what sine is when we talk about right triangle trigonometry. And when I'm drawing right triangles, let's actually draw them like this with the right angle in that bottom right hand corner. Because now, right there, that angle will be our central angle. And what's really nice about that is even if I'm stuck in the unit circle or not, ratios still hold. And the angle itself doesn't matter about how big the radius was that I was trying to extend. I've just got myself somewhere in space where there's the origin. Okay? And I don't care how big that hypotenuse length is, how big this x value is, how big this is, the relationships will still hold whether I squish this triangle back down or I stretch it out. And what this idea allows us to do is draw, like asking questions like this, allows us to draw right triangles that make that shape. And we're always, always, always here in the first quadrant going to draw them like this. Because now if sine of theta is opposite over hypotenuse, there's the hypotenuse, right? There's the opposite side, there's the adjacent side, right? Hypotenuse always across from the right angle. Opposite is the side directly opposite, right? And adjacent means next to. So there's the side that's next to the angle that's not the hypotenuse. What I can do is I can label this triangle. I know that opposite over hypotenuse is 3/5, which means I can write in a length for this opposite side. I can write in a length of, in this case, a 3 for opposite and 5 for the hypotenuse. Yeah, I'm not in the unit circle anymore because, yeah, the radius is now 5 instead of 1. That's okay because the proportions are still true, right? We can draw a right triangle based on the ratio that's given as long as we draw that angle coming out from the center. Okay. So how are we going to figure out cosine? Well, cosine is adjacent over hypotenuse. And so all we really need, I'm going to slide us over here. All we really need to be able to do, hopefully, is find the length of that adjacent side. Okay? Is there some sort of formula, some sort of relationship that connects all 3 sides of a right triangle? The relationship between sides in a right triangle. I'm just going to draw a triangle with a little right angle here. Do you know a way to relate the 3 sides of a right triangle? In one formula, one equation that's always true? Starts with a P.
Pythagorean theorem.
Good. Okay, now Pythagoras is the guy that's credited with this, and if I had 6 days of time with you, I could tell you so much about how crazy and amazing this guy is. I'll just tell you this, he started a cult and got kicked out of Greece. We'll just start with that, okay? The Pythagorean theorem, okay, THM, gives us a relationship a squared plus b squared equals c squared. Always gonna work here in right triangles. So there's a leg, right? Doesn't matter A or B, they're interchangeable. C is always your hypotenuse, right? So it's really leg squared plus leg squared equals hypotenuse squared, right? Okay, 3 squared plus, I don't know what that is, right? I'm not sure what that length is, right? Some leg, b squared is equal to 5 squared. Okay, 9 plus something squared equals 25. Subtract 9 on both sides. If the length of this squared is 16, then the actual length, of course, is just the square root of that, which is 4. Okay? And what we have is a really, 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 really nice right triangle that, although this angle is not all that pretty, right, 36 point whatever, the sides, really nice. They come in 3 of them. Obviously, there's 3 sides in a triangle. They come in a triple, and they're all integers. Okay, 3, 4, 5 is one of those. And make this as big as you want. Call it 6, 8, 10. Right, double all the sides. Still going to work. Multiply them all by 10, 30, 40, 50. That triple would work as well. And there's actually something called the Pythagorean triples, which are side lengths of right triangles that are all integers. Okay, side lengths. Let me just say integer only side lengths in right triangles. And every time I do a right triangle, I'm just going to draw. Okay. And there are 4 main ones, okay? 1, 2, 3, and 4. Now, there are an infinite number of them because you could just multiply 3, 4, 5 by 1, by 2, by 3, by 4, by 5, by 6, by 7, and all work, okay? So 3, 4, 5 is a Pythagorean triple because they're the integer-only side lengths in the right triangle. And of course, all of their multiples, okay? There are a couple other ones that are really nice to know, okay? 5, 12, 13 is another triplet whose side lengths, when you square this one plus this one squared, is going to be equal to this one squared. 25 plus 144 is 169. Okay. 7, 24, 25 is another good one. And 8, 15, 17. You don't have to have those memorized, but it is nice to have them somewhere so that maybe you don't have to do the Pythagorean theorem every time if you're seeing a ratio like this and you need to figure out that last missing piece, right? Because now, oh, cosine of theta, well, that's just adjacent. Over hypotenuse, that's 4/5. And I don't know what the angle is other than inverse sine of 3/5 or inverse cosine of 4/5, right? Or inverse tangent, opposite over adjacent of 3/4. Okay? And we've got really nice triples that help us avoid having to do the Pythagorean theorem over and over and over again. 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17, which of course, the last number, the biggest one, has to be the hypotenuse. Okay? So, what are we trying to accomplish here? The idea behind 4.3 is to remind you that SOHCAHTOA is a thing, right? That we have relationships in right triangles, right? It doesn't matter whether we're in the unit circle or not, where the side lengths are in proportion, right? And that's kind of what it all comes down to. But the other thing that we want to make sure that we're able to do is if we're only given one trig ratio, whether it's sine, tangent, cosine, whatever, it's giving me 2 sides of a right triangle. And if I have 2 sides, I can always find the third, okay? That's what I want us to be able to do. I saw a question. I know I just walked off screen. I wanted to take pictures of the board before I erased it. I saw something in the final for this semester's college trig class with questions that looked like these. And so here, let me do it like this. Trying to get it all in one shot here for number 3. Cool. Before I erase it, I saw something in that college trig final that had questions that were designed to resemble questions that look like this. Okay, where it all came down to recognizing what was given. Right. So they give me sine of theta equals 3/5. Really, what's given, right? You probably that might be too glary up there. Really, what's given is that some angle is the inverse sine of 3/5, right? They're saying, I don't know what the angle is. It's irrational. But what I tell you about it is that, so the opposite length is 3 and the hypotenuse is 5, okay? And then they ask us to kind of use that to make some sense of what's going on, okay? So let me do one more thing with you about these, and then I'll tie things all together so that basically most of chapter 4 is done up to this point. Okay. Okay. So call this one number 4. All right. Let's say they give us that the cosine of some angle is 12/13. Okay. If they give us a setup like that, and they don't ask us necessarily for what the actual angle is, because we won't be able to tell, right? If this isn't a unit circle spot, meaning 1/2, radical 2/2, radical 3/2, things like that, I know that there's a pretty good chance that whatever theta is, right, the inverse cosine of 12/3, there's a pretty good chance that that's just going to be irrational, and there's the best way for me to do that. But what I want to be able to answer are questions maybe like this. What's the tangent thing? Okay. And to do that, I have to have a good understanding of how to draw. So step number one, draw a first quadrant. So Q1, right triangle. That's not a right triangle. Right. Okay, so that's what I'm gonna do. I'm gonna give myself a space where this thing can exist. And whether you draw the axes or not doesn't matter. I really just want to give myself some sort of shape that's going to do what I need, right? And I'm always going to draw my right triangles in the same orientation, with this being the origin and my right angle being on the bottom. Okay, so it's going to look just like that. Okay. Step two is to label two of the sides based on, okay. And if they're giving me cosine, C-A-H, what I know is that compared to this angle right there, that theta right there, so I'm just here right now because they gave me cosine, 12/13. 12 is the length of the adjacent side, and 13 is the length of the hypotenuse. Guaranteed. Right? And I could squish that down if I really wanted to, but why go so crazy and call this 12/13 and call this 1 and stick myself in the unit circle if I don't have to be, because this angle is not necessarily a nice one, right? What I want to be able to do is answer the question, what's tangent? Okay? Now, in order for me to do that, we need to find the missing side. Okay, and all that takes is a Pythagorean theorem, or, if we're lucky, a knowledge of a Pythagorean triple. And they love to use Pythagorean triples to save us some time if we recognize them. Do you recognize or remember or can look back at a Pythagorean triple that has 12 as one of the legs and 13 as the other? If so, what's that last side?
5.
Okay, 5, 12, 13, guaranteed. And now that I have that, now I can actually answer the question. Okay, now I can answer whatever the given problem was, like what's tangent of theta? Well, tangent of theta, SOHCAHTOA, is just the length of the opposite side over the length of the adjacent 5 terms. And yeah, if they wanted to know what theta is, sure, fine. It's the inverse cosine of 12/3, or it's the inverse tangent of 5/12, or it's the inverse sine of 5/13, right? There's a lot of different ways to say the same thing, because we have so many relationships within trig, which can be a little heavy to carry all of those relationships on your shoulders, but it does give you options, which I'm always a really, really big fan. Okay, so questions like this are really, really nice. Now, one way that they could present this to us, call this number 5, is they could combine these two things together. Okay, because theta is the inverse cosine of 12/3. And what they might do is they might create one expression that has all of that information stuck all together. And here's what I mean. So maybe they could have said something like, the sine of theta equals 8/17. And the question that they're asking for is the cosine of theta, right? Maybe they present it like that. Or maybe they do something a little bit sneaky. And they say, you know what? Well, if the sine of theta is 8/17, then theta is the inverse sine of 8/17. And they combine these two together. Okay, so maybe the question really looks like this. Cosine of, and I know if it's regular cosine, what's going to happen in here is an angle. But they specifically could say the inverse sine of 8/17. Right? And I know that that's going to be an angle, right? Because you're giving me the ratio and I'm going to get an angle back. And when I'm dealing with regular trig, what goes in is an angle and what should come out is some ratio, okay? And so what we do, if given a setup that looks like this, is we treat it exactly the same as all of the problems that we've done so far, that I go back to these steps 1 through 4, and I can start to build a way to visualize this kind of question, okay? And when you recognize a ratio that is not a unit circle ratio, the best thing to do is to draw a right triangle, okay? And with the first quadrant orientation, having the angle down here, the right angle over here, it makes it pretty easy to recognize all of these pieces. Okay, so it can get tricky, and we'll come back to this for sure when we get back in January, but I wanted to give you this before we left, okay, so that it was kind of stuck in your brain and we can always come back to it, okay? So now, all right, draw a quadrant 1 triangle. Now, what do I know about 2 of those sides? Well, I always work from the inside out, just like we did with like composition of functions, right? You had f of g of 3. Okay, I'm going to do g of 3 first. I'm going to take care of what's inside. I've got these double sets of parentheses and start to build my way out from there. What I need is a basic understanding of SOHCAHTOA and what that tells me about the sides of the triangle that I'm in, okay? Sine is opposite over hypotenuse. And so if 8 is the opposite length, I can draw an 8 right there. And if 17 is the hypotenuse, that means I can draw 17 right there. And step 1 and step 2 are done. Step 3 says, well, let's find that missing side. Okay? And if I'm in a right triangle, Pythagorean theorem always works, but if you recognize 2 of the numbers within a Pythagorean triple, and they're in an order that makes sense, where the hypotenuse is definitely 17, because I know that, because that's what was given to me, maybe, just maybe, we can figure out what this missing side is without having to do the Pythagorean theorem, but just knowing a Pythagorean triple, right? 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. Okay. Now, sure, this is some angle. Which angle? That one, right? It's this angle within this triangle. And now I can really answer the question, what is the cosine of this angle here in this triangle? And although it could be a little misleading to see what's happening, once you draw that picture, you can really just say, okay, what's the cosine of theta? Okay, cosine of theta is, well, so COA adjacent over hypotenuse 15 over 17. Okay? Again, they're not telling us to go find exactly what the angle is. They know exactly what the angle is right here. It's some inverse sine of 8/17, right? Some weird, am I still sharing? Somebody's got to tell me that so you could actually see. My goodness. You got to speak up. You can probably barely see that. There we go. Okay, here we go. Here we go. Now we're good. Hopefully somebody's talking to me. Why was the first problem cosine and the second problem tangent? What do you mean, Morgan? You mean like going back to number 4? What do you mean? It's like one big problem within one triangle. Okay, so number 4 and number 5 are two different triangles, two different problems, but they're presented in a way that we follow the same process. Whether they give us two separate pieces of information, one of the ratios and 2, the ratio they want us to find, or, right, one ratio and like one given ratio and one ratio to find, or they present it in a way that's all together with one expression that does both. The inside telling us what the ratio is and which ratio to look at, that helps us draw part of the triangle, right? It allowed us to draw that part of the triangle. And then asking us, okay, once you have your triangle, give me the cosine of the angle that makes that work. Does that make sense? Like the idea here is they might present it one of two ways. Like, here's a ratio, yay, draw a triangle. Okay, here's the question, two separate things. Or they could make it one expression, and they say evaluate cosine of whatever this is. Well, whatever that is some angle in a right triangle, 4.3 right triangle trig, where I can draw two of the sides, and if I can draw two of them, I can find the third. Hopefully it's a Pythagorean triple number, so I don't really have to do anything except to find it. And then follow SOHCAHTOA to get me there. Okay, cool. All right. So I just wanted to, and we're not going to flesh this out in a huge way just yet. We're not going to get to the point where we're going to do a ton of practice with this. There was one question on the college trig final that looked like this, so I didn't want to spend too much time on it. But I just wanted to show you a couple things about how great the unit circle is, but how limiting it can be as well, and how it can be a lot easier sometimes to deal with relationships like SOHCAHTOA when we're in a right triangle trig. And we're in some kind of right triangle when we're doing the trig with it. But obviously those are just the three basic trig ratios. We've got their reciprocals too, and that could always come up. And this is one of my favorite things in trig to say out loud, like the SOHCAHTOA version of cosecant, secant, and cotangent. I'm just going to put them in the same order, right? So secant, sine, its reciprocal is cosecant. Cosine, its reciprocal, man, my words today, secant, and the reciprocal of tangent is cotangent. So I'm just going to use the same first three letters that they did there, and I'm just going to switch the letters, right? So it was opposite over hypotenuse, so now it's hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. If these are your three basic trig ratios, this is a way to remember all of the reciprocals. SOHCAHTOA, CHOSHACOW, which is just way too much fun to say. I just cannot get enough. CHOSHACOW is how I would say that out loud, and we can use those as well. So if you had like the inverse secant of 5/4 or whatever, you can figure out a triangle from there, okay, by doing CHOSHACOW, which is crazy. Okay. Okay, so a couple last things to just have down somewhere so that you've heard it before January, okay? There are some really nice things that we can use to continue to make connections between one trig function and another, right? Here was one really good example. You can relate sine and cosine together by drawing one triangle, or cosine and tangent, or secant and tangent, or if there's always a way to find, if you give me two of the sides, I can find a third by doing some right triangle trig, okay? And that's really nice, and we really, really like that, okay? And there are some other ones too. There are some other ways that relate one trig function to another, or more than one, okay? And when I talk about relating things together, they happen in a way that's always true, okay? That no matter where you are, no matter how big or small your angle is, no matter how big or small the triangle is that you're looking at, these relationships will always, always, always be true, okay? And we call those trigonometric, or just trig, identities, okay? Trigonometric identities, okay, are relationships between trig ratios that are always true, okay? No matter what, no matter where you are, no matter how big things are, how small they are, some things that are always true. Like cosine is in a right triangle opposite over hypotenuse, or adjacent over hypotenuse, right? Sine of theta is equal to y if you're in the unit circle. Cosine of theta is equal to x. That tangent is equal to y over x. And if tangent of theta is equal to y over x anywhere, and sine is y, right? Y over x, and sine is y, and cosine is x. Well, then tangent of theta is always sine over cosine. Always, 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 always. And cotangent is just the reciprocal of that, cosine over sine. Okay, that always, always, always true. Those are called the reciprocal trig identities. Okay, sorry, the quotient fractions, quotient trig identities. Okay, the reciprocal ones are like sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals of each other. These are the quotient trig identities because they're made up of two trig identities, trig functions as fractions, okay? Those are really nice, okay? And I'm gonna leave you today with just one more set of trig identities, okay? And they're called the Pythagorean identities. Since we're on a Pythagorean kick here on this lovely Thursday, let's finish with these, okay? Anywhere in the unit circle. Now, and remember, all of these angles we've been dealing with, yeah, they're in the unit circle, they're just nasty, right? There's really not nice radian or degree measure, but they're in there, right? They're all angles. Anywhere from 0 to 2 pi, it's all in there. Pick an angle anywhere you want inside the unit circle, and I don't care where you are, right? Could be in the first quadrant, second, third, fourth, doesn't matter, okay? What we know is that that point right there is cosine of theta, sine of theta, right? Every xy is cosine sine. And the other thing that I know is that the radius of that circle is 1. But what else do we now know that we can do is we can pull that right triangle that exists right here, and I can pull that out and deal with it separately. Right? There's my right triangle that I could draw based on whatever angle I just opened right there. Where the x length is cosine, the y length is sine, and the radius is 1. And if that's what I know for sure, if I know that anywhere, any angle I want, right? Things that are always true, here we go. We, in a right triangle, can use the Pythagorean theorem. Now, Pythagorean triples are really nice because then I don't have to, Okay? But what I do know is that I've got a way to relate cosine, sine, and 1 within a triangle. Okay? Because I know that a squared plus b squared is equal to c squared. And what I can write, and don't write this just yet, okay? There are 3 Pythagorean identities, okay? One of them starts like this, where I take sine and I square it. I take cosine and I square it. I take 1 and I square it, and I add them all together. The tricky part about how to write this, and again, this is the part that I don't want you to write just yet, that if I take something like sine of theta and I square it, if I put the parentheses around the sine and put the 2 on the outside, sure, that's great, but there's a lot of parentheses there for me just squaring one thing, right? I would love to figure out a way to drop these parentheses so it would be easier for me to write the exact same thing. But again, don't write this yet. This could be a little misleading in what we think might be squared in this problem. It's not that I'm squaring the angle. No, I'm squaring the sine of that angle. I'm squaring whatever that distance is right there. And so when we write trig ratios like sine, cosine, and tangent and all the reciprocals, when we write them squared or to the third or to the fourth, we don't put the square at the end. Because we might think that it's the angle that's being squared and then we take the sine of that. No, I want to do sine of theta and then square it and see what happens. And so here's where we write our exponents. We write them in between. Sine squared of theta really just means sine of theta squared, right? Here comes the Pythagorean theorem. Sine squared, so one length, plus the other leg squared. Okay, cosine squared theta is equal to 1 squared. Well, what's 1 squared? Sine squared plus cosine squared is equal to 1. Always, always, always pick any spot you want, any angle, anywhere, and you will find that sine squared plus cosine squared is equal. Okay, crazy stuff, but it works out, which is so cool. All right, so that's one. Okay, the way to create the other two that gets tangent and cotangent, secant and cosecant, the way to get those in there is to take this identity and mess with it. Okay, and that's the last thing I'm going to show you. Okay, again, we're not going to play around with what we're going to do with these just yet. I just want you to have them down so we can come back to it. Okay, so I'm just going to come over here so I can mess with it. Sine squared theta plus cosine squared theta is equal to 1. That's definitely true. Okay, and if that's true, well, if I added 5 to both sides, it would still be true. If I multiplied by 2 on both sides, it would still be true. If I divided by 10, it would still be true, right? Because it's an equation. And as long as I do the same thing to the left as I do to the right, I'm good. As long as I'm not like dividing by 0, right? And so that's what I want to make sure I do, okay? What I'm going to do here is I'm going to take everything on the left and everything on the right, and I'm going to divide by something, and I'm just going to make sure it's not 0. And what I'm going to choose to divide by is one of these 2 trig ratios that's being squared. Because I just want to turn like one of these into 1. Okay, so here's what I'm going to do. I'm going to divide everything, and I'm just creating identities here. Okay, I'm going to divide everything by sine squared. And watch what happens. Sine squared divided by itself. Anything divided by itself is 1. Okay, so 1 plus. Well, cosine squared over sine squared. Well, okay. Get rid of the squares for a second in your mind. Which trig ratio is cosine over sine? Oh, cotangent right here, right? And so if cotangent, regular cotangent is cosine over sine, then cosine squared over sine squared, that's going to be cotangent squared, right? And 1 over sine is cosecant, so 1 over sine squared is cosecant squared. And there's another trig identity that 1 plus the cotangent of any angle squared is equal to the cosecant of that same angle squared. Okay, crazy. And all of these work really well. Let's get ourselves one more by dividing everywhere by cosine squared. And then we're done. You got a really good background. Sine divided by cosine is regular tangent, so sine squared over cosine squared is tangent squared. Cosine over cosine is 1. And 1 over cosine would be secant, so 1 over cosine squared is secant squared. Ta-da. There you go. Okay, last ditch effort for me to get you some really important basics on how to deal with stuff with the right triangle trig in 4.3. So I would say by now 4.1 through 4.4 is basically done. And you just did that in a week. That's awesome. So thank you guys for being here. Nothing you need to do from here on out. Welcome to, if you'd like, the end of first semester here in Oxford. Okay, you're done. Okay, I'm not going to assign any homework for you for tonight. What I will do is I will send out something optional. Okay, if you're looking for some extra credit, because I asked a little bit yesterday about what we want to do between now and class on technically Monday, right, when we have our final. I'm going to send something out that's optional and extra credit. It won't be a ton, but it's for those of you that are like right on the edge, like less than a point away from maybe getting yourself to the next letter grade. Maybe this could do it. Maybe not, depends on how you do, but I will send something out that kind of wraps up everything that we've done so that you'll get it probably like later today or tonight, and it won't be due until the day of the final, okay? So look out for that. And remember, it's optional, so that if you are good and happy with your grade and you want to focus on other things, you can do that. If you want to give yourself just a little bit of a boost. And also make sure that all this stuff kind of ties together, because we really didn't practice this with a lot of meat today. You can do that as well. All right? Other than that, good luck next week. I hope you guys do really, really well on whatever finals you have. I hope you have a great, great, great winter break. If I don't see you live, I'd love for you to just stop by Monday morning so I can take attendance and just see you and wish you good luck. But other than that, have a great break. Stay safe, have fun, and let's come back in January refreshed and ready to go. Thanks, guys. See ya.
Bye.
Bye, thank you.
Bye. Thanks, everybody.